Okay, guys, we're going to talk about thermodynamics. Make sure you watch this to the end, and then all we're going to do on Thursday is work problems in this. So this is just like a stupid, funny joke, but it's about energy and Tokyo and Wyoming. And of course, I thought it was a gorilla that took over Wyoming, or I'm not Wyoming, Tokyo, but I guess not. Anyways, okay, so thermodynamics in and of itself is the study of the energy that's occurring, the work that's occurring, the heat that's occurring and its changes when reactions happen. So if you've seen any kind of action film ever in your life, you've seen, the car blow up and the people go, and they fall on the ground. Or, if a building blows up, the big plume of smoke and the fireball that happens, all of that is energy being dispersed through anything. So when we talk about energy, we're going to be talking about thermal energy for these purposes. I'm going to be interchanging the terms heat and energy synonymously. And so energy, when we're talking about it in this capacity, is anything that has the capacity to do work. So energy is in everything, even the computer that you're looking at. Obviously you think, oh, okay, the motherboard and the processors and the hardware and software, they're all doing something. You can feel sometimes your laptop gets hot, it's heating up. But I mean, even the plastic it's made out of, even the desk that your laptop is sitting on, these all have energy to some extent. Whether or not it's work energy or potential energy are two different things. So work in general is the force acting over a distance. If you had any physics class, you remember work, and it's force times the distance. So heat, we're going to refer to as the flow of energy. A lot of times, especially here, in the summertime, we're saying, gosh, it's just so hot outside. And we talk about temperature as, synonymously with heat. Those are two different things. Temperature is not heat. Temperature is a measure of something, where heat is flow of something. So heat, for our purposes, for this thermochemistry section, is going to be the flow of energy, and it's caused by a difference in temperature. It's one of the basis, actually, for many of these supercell storms that we've been watching happen and increasing over the past 7 or 8 years or so. Now, we can talk about energy being exchanged or changing type, but it is never, ever created nor destroyed. It just is. It is equal. So one of the things we can say is, as far as the first law of thermodynamics, is that the total energy of the universe is constant. That's the first law. The first law of thermodynamics is not conservation of energy. Conservation of energy is a characteristic of the fact that the total energy of the universe is constant. So what does that mean? That means energy cannot be created nor destroyed. We just don't say, poof, here's energy, or poof, here's, not energy. What we do is we say it changes, and it goes between objects. Any studies you've ever watched at all or ever heard about, think about car seats. Why are car seats so important? Obviously, main answer is they keep babies safe, or toddlers or small children safe. Well, why? The reason is everything in a car is traveling at the speed the car is traveling. So if you're driving on 95 and you're going 70 miles an hour, your cell phone, your purse, your jacket, your hat, your jewelry you're wearing, it's all traveling at 70 miles an hour. When cars collide and hit because there's, say, a car accident, then the energy from car A is transferred through car B. And the reverse is true for car B. That energy is transferred through car A. This is why, for example, when we're traveling at 70 miles an hour and there's a head-on collision, the outcome is often devastating. But if we're traveling at 5 miles an hour, it's a little fender bender in a head-on collision at 5 miles an hour. In fact, head-on collisions at 5 miles an hour, we don't even classify as head-on collisions. We call those fender benders, right? Even our terminology for our everyday usage is different. So if energy is the capacity to do work, what does that mean? Well, we have two things. We have kinetic energy and we have potential energy. With kinetic energy, that is the doing of the work. The potential energy is just like it says, it's the ability to do a certain amount of work. So I have the potential when I'm sitting on my couch to get up and go do work on the elliptical. Those are two completely different things. And the amount of energy I have sitting on that couch to do work on the elliptical doesn't change. It's there. So let's say I can do 45 minutes on the elliptical. I have that potential sitting on the couch. Well, once I get up on that elliptical and do the work, it's in me to transfer it or to change that potential energy into the working of the 45 minutes on the elliptical. And we see evidence of that with, for example, kinetic energy in things like thermal energy. So when I'm on the elliptical and I'm doing 45 minutes, I sweat, right? Or I get sore, or I can feel it. The potential energy, I don't really feel anything, but it's a chemical energy that's present. So the ability for my body to do it is in my body. Once I start transferring and shifting that potential to doing of the work, kinetic energy, that's when there's a transfer. So again, first law of thermodynamics. It is not law of conservation of energy. That is a characteristic of the first law, which is the total energy of the universe is constant. Because the total energy of the universe is constant, that means energy cannot be created nor destroyed. It can only be converted from one form to another. So what does that mean? What that means is, on a chemical level, kinetic energy is the doing of the work, potential energy is the potential work it could do, and heat is either put in or taken out of that system. But what that really means on a more basic level is, if I were talking, for example, about a flashlight. In a flashlight, we have batteries. We have a little button that makes it work. Click on, click off, and light comes out. Now, if you think about it, the pressing of the button causes there to be a connection of the battery to circuits that allow the light bulb to light. There's chemical energy in the battery. The light bulb lights. And when the light bulb is lit, heat is being radiated. That energy is not poof gone or poof there. It just is. How many times do you have a cell phone for more than a year, and after a while your battery can't keep its charge for, more than a couple of hours, when in the beginning it was like 10 hours and you were good? Let's negate for a second background processes and apps that are running. Okay, let's just talk about battery life in general. Every time you buy a cell phone, every time you talk to a cell phone carrier, what do they tell you? They say, let your battery drain all the way to zero before you ever plug it in again. Do we ever do that? No, of course we don't. We're like, oh, it's at 60%. I got to plug it in. We don't wait till it's at zero. And what that does is that removes the ability of the battery to do what it needs to do to be fully charged and to be at its peak capacity, to be at its ultimate operating phase. Okay? So it's not that energy is lost. In some regards it is. It's lost, but it's lost to the environment. So I've talked a lot about, so far, the environment, poof created, poof not created, changes, all these things. The bomb explosion, energy going out into the air, as we can see, like even on a really hot day on the pavement, you can see kind of the heat waves coming off the road. We need to define a few things, and that means system and surroundings. So system, we can define as anything in the universe we want to define it as. It's the material or process within which we are studying the energy changes. Okay, so what does that really mean? That means we're looking at something. There's some reaction happening, some thing that is occurring that we're looking at. That's the system. Everything else is the surroundings. and everything outside of that is the universe. So let's just break this down a little basic. When we're in our classroom and we're lecturing, our classroom is the system. That's what we're doing. That's what we're working on. The building we're in is our surroundings, and the whole rest of the world is the universe. So this system versus surroundings are very defined things. I could say in the lab, my test tube is the system, the lab is the surroundings, and the building is the universe. I define it however I want, but it's a very specific thing. So the system is where the process is occurring. The surroundings are everything else, and the universe is everything else around that. It's between the system and the surroundings that an exchange of energy is occurring. So the system can be exchanging energy into the surroundings, or the surroundings can be putting energy into the system. Think of water in a pot on a stove. Okay, if I turn my stove on, then heat is being put into that system of the pot of water, and eventually the water will boil. Likewise, if I grab, or let's not say that, let's not say grab. If I put an ice cube in a hot bowl of soup, that ice cube is taking in heat from the system, therefore the system is cooling down. So when we talk about units of energy, we're going to talk about it a couple of different ways. These energy conversion factors, you have to know. You have to memorize these. So first of all, kinetic energy, we can quantify with a kinetic energy equation, which is 1/2 the mass times the volumes squared. Velocity squared. So 1/2 mv squared. Our units for kinetic energy are going to be kilograms meter squared per second squared, which by the way is also equal to 1 joule. So kilograms meter squared per second squared is equal to 1 joule. Those are our units. So we're either going to be using this one or this one. In our problems, it will just depend on what it is we're dealing with. Calories is the amount of energy needed to raise 1 gram of water by 1 degree Celsius, and everything has its own calorie assignment, but we usually use it in reference to water. So energy needed to raise 1 gram of water by 1 degree Celsius. That is a calorie, lowercase c, which is differentiated from food calories we get from what we eat. Kilocalories are the energy needed to raise 1,000 grams of water, 1 degree Celsius. The metric prefixes all stay the same here. They are all, kilo is the same as the kilo is kilometer or kilogram, etc. It's 1,000. So you need to know that 1 calorie is equal to 4.184 joules. 1 capital C calorie is equal to 1,000 lowercase calories, which is equal to 1 kilocalorie, which is equal to 1,184 joules. 1 kilowatt hour, 3.60 times 10 to the 6 joules. You need to know these for a test. So in terms of energy, what we said was, as a definition for the first law of thermodynamics, the total energy of the universe is constant. So what we do is we look at it in terms of changes between the system and the surroundings, which are equal to the net of the energy of the universe. So the net energy of the universe is equal to the system plus the surroundings. Whatever changes in the system happen plus the changes in the surroundings. And the delta symbol, I think you should know by now, means change. It's always a final amount minus initial amount. Yes, there's a plus sign here, but one of these will be a negative value. So it will be basically plus a negative, right? All right, so let's talk about this. Internal energy, the sum of the kinetic and potential energies of all the particles that compose a system. The change in the internal energy of a system only depends on the amount of energy in the system at the beginning and the end, blah, blah, blah. What does that mean? What that means is the total energy of the universe is the difference between the changes in the energy of the system and the energy of the surroundings. None of that is dependent upon how it got there. So again, let's break this down kind of Barney style. If I were to walk from campus, from our building on campus to the cafeteria, okay, I could beeline it straight, diagonal, geometry style from our building right to that building. It would be the least amount of energy, the least amount of everything. It wouldn't, the energy I exerted versus saved would be a certain amount. Or I could start at our building, go up to the Hargrave building, go across the fountain, come around, follow the sidewalk, go back by, that back road there, how you get to the, where you get your decals at where the dorm entrances are, come back around and come in the back side of the cafeteria building. Now, is it a much longer, convoluted way to get there? Sure. In the end, do I end up at the cafeteria? Yes. So things that are state functions, the difference only matters with the initial and final values. Building that we do lecture, building at the cafeteria. It does not depend on the path we take to get to that building. Okay? So anything that's a state function only relies on building A to building B, not the pathway to get there. So for this, for what we're talking about here, state functions are things that it doesn't matter how you, in the end, change the energy. Why does that matter? Well, because some things are stepwise reactions. Some reactions have intermediates. Some reactions use more energy or less energy, to get from point A to point B, but in the end, you get from point A to point B. So here's just another example of that, a state function. So a state function is a function that the result depends strictly on the present state. Where are you? In our case, a present state for chemicals is a condition of the system. So we don't care how we got to that condition of the system. You guys see that in lab all the time. Some of you are there for an hour and a half. Some of you are there for 20 minutes. In the end, y'all got the end results. So if I wanted to go, say, from Castroville, California to Boston, Massachusetts, whether I go all the way loop-de-loop or whether I go up here or whether I go straight across, none of that matters. I start in one place, end in another. So in terms of the universe, why does this matter? Well, if the final condition, this is what it says, if the final condition has a larger amount of internal energy than the internal condition, the change in the internal energy will be positive. Blah. Okay, that makes sense. If my initial positioning is lower energy than the final, it's going to be a positive delta E. But remember, we're talking about chemical reactions. Things react for the purposes of getting to a lower state of energy. That's always the goal. That's always the most stable. That's always the best way to do it. So if the final condition has the least amount of energy, there'll be a negative delta E. So again, we know this makes sense, final minus initial, etc. But why? Where does it really matter? Where it matters is the way the energy flows. So when we're seeing energy leave a system, the only place it is going is into the surroundings. So what does that mean? That means two things react together, and the reactants individually have a higher energy level than the product they produce when they react. So it's releasing energy, and that energy goes into the surroundings. When energy flows out of a system, the delta E of the system is negative. We often see that as more favorable. When the energy flows from the surroundings into the system, it's positive. So what we say is the change in energy of the system is the negative change in energy of the system is equal to the energy of the surroundings. So whatever I put in, I get out. If it takes me, let me rephrase that. If it takes negative 177 joules to be released from a system, then the surroundings is going to accept 170 joules. Okay? So here, just a little, you might want to, I don't know, copy and paste this into something or write it down. So when the change in energy of the whole system is less than 0, if it's negative, then the system is flowing into the surroundings. The energy of the system is flowing into the surroundings. When the energy of the surroundings is greater than 0, then it's accepting the energy from the system. So here's an actual example. We have carbon, solid carbon, and oxygen gas. And those are the reactants. And they're going to form carbon dioxide. That's just the chemical reaction. That's the system we're looking at. Everything else is the surroundings. So when this happens, carbon dioxide, you can see from this diagram here, it has a lower energy than the individual carbon and oxygen by itself. So the total amount of energy with each individual reactant, it's higher than the total energy of carbon dioxide. That's why this is a favorable reaction, and it'll happen naturally. Energy is released because this is higher, this is lower, so there's a negative energy. That means energy is going to be released into the surroundings. When there's a negative energy in the system, it gets released into the surroundings. The reverse of this, where I'm going from carbon dioxide back to the individual reactants, breaking it apart, right, in a decomposition reaction, we get a positive change in energy. So that means now the surroundings are putting energy into the system. So let's just look at this energy exchange generically. When we exchange energy between the system and the surroundings, it's going to happen through heat and work. Heat, we use the lowercase letter q to represent heat. Work, we use a lowercase kind of italicized w. Q and w are not state functions. Their value actually does depend on the process. And you know this any single time you've had to run a mile or gone on an elliptical. Yeah, heat and work, they matter in certain circumstances. The more work you do, the more energy you're expending. It's tough. These are not state functions. So when heat, Q, when the system gains energy, delta E is positive. When the system releases heat, it's negative. Why? Because we can surmise the change in energy of the whole universe by the amount of work plus heat. Q plus W. Heat for Q, heat, W, work. Adding these together will give us the total change in energy. So mathematically, you can see how if this one is positive and this one is negative, I'm sorry, let me just start over. If this one is positive and this one is positive, overall it's going to be positive. If I get a negative and a negative, overall it's negative. If I get a negative and a positive, well, you're going to have to see which one is bigger, right? So here's just a little example, pool example. The white ball, the cue ball, let's just say it has an initial amount of 5 joules of kinetic energy. Okay? As it rolls on the table, and for us in here, we're not going to worry too much about this. We know that some of the energy is converted to heat by friction. If you've had any physics class, you remember doing it's got 5 joules, but it's losing it to the table and to air resistance and all that kind of stuff. We're going to kind of ignore that a little bit. But the rest of it is transferred to the purple ball when it hits it. So we're going to hit the cue ball, at, say, 5 joules, it hits the purple ball and the purple ball moves. It's transferred. What energy is left after rolling here is transferred to this purple ball. And that ball rolls with a certain amount of energy. All right, so here's just a brief example. If the burning of fuel in a potato cannon performs 855 joules of work on the potato and produces 1,422 joules of heat, what is the change, what is the delta E for the burning of the fuel? Well, here's our generic things. Heat of the system is equal to the negative heat of the surroundings. We just talked about that, right? Whatever the system gives off is equal to the amount the surroundings takes in. That is true also of work. So work of the surroundings is equal to the negative, system is equal to the negative work of the surroundings. So whatever work the system does is equal to the work the surroundings takes in. Because of that, we get the change in E, delta E, is equal to Q plus W. So what are we doing? We're simply saying, okay, the burning of the fuel in a potato cannon does 855 joules of work on the potato. Okay? Work of the fuel is equal to work onto the potato. Because of that, it produces 1422 joules of heat. Heat of the fuel produces heat of the cannon. Plug and chug, you get your answer. Okay, so the total change in energy for this, the fuel burns, the cannon performs a certain amount of work onto the potato, and therefore produces so much heat. So the reaction is producing, these numbers we're not going to talk about this just yet. These numbers indicate that the change in energy is negative. So what that means is it's favorable. Remember, if you go back, here, if the product formed has less energy than the initial reactants and their doing of the work, then it is favorable. Okay, let's look at this one. You have a reaction that produces 3.1 times 10 to the 2 joules of heat, and the decrease in volume requires the surroundings to do 7.6 joules of work on the gases. What is the change in internal energy of the gases? Well, let's look at this. Again, same equation. Delta E equals Q plus W. We know that the amount of heat is Q. Q is our heat. Here is our heat. 3.1 times 10 to the 2 was just changed to 310. And 7.6 joules, that's the work, right? But how do we know that's negative? How do we know that's positive, etc.? Well, let's look. The reaction produces heat. That means it's going from the system into the surroundings. And the decrease in volume requires the surroundings to do 7.6 joules of work. So based on Q of the system equals negative Q of the surroundings, if we say it produces, that means it's going from the system into the surroundings. That must be a negative number. The decrease in volume requires the surroundings to do 7.6 joules of work. So we're talking about the surroundings. We know that's the work it's doing because that's what it told us. If the surroundings are doing the work, it's positive. And the surroundings took the heat. Heat of the system equals negative heat of the surroundings. Add them together and that's your number. All right. So Heat capacity, you have to know this as well. Heat capacity is the amount of heat required to raise the temperature of an object or substance a given amount. We look at it in terms of Q equals capital C, that is the heat capacity, times the change in temperature. So much like a specific heat or a density or any of those constants, every individual thing has its own heat capacity. And oftentimes that'll either just be given to you or you'll have to be able to figure it out based on the information given in the problem. So we can figure out the amount of thermal heat, Q, based on the heat capacity times the change in temperature. Molar heat capacity takes into account the amount of moles present. So the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. This is our heat capacity, our molar heat capacity, times the moles of a substance, times the change in temperature. Specific heat is the amount of heat required to raise the temperature of 1 gram of something, doesn't matter what it is, by 1 degree Celsius. And each individual thing, whether it's an element or a compound, they all have their own individual heat capacities, molar heat capacity, and specific heat. Specific heat we're going to use the most frequently, and it's going to be the specific heat of that thing times the mass of it times its change in temperature. So when we talk about specific heat capacity, and we talk about, the amount of heat energy required to raise the temperature 1 gram by 1 degree Celsius, you can see from this little table here, lead has a different, well, they're same value, but if we went out and carried it out several more decimals, they'd be a little bit different. But, they're different than silver, different than copper, iron, aluminum. All of these things have different specific heat capacities. Molar heat capacity, again, the same thing. Everything has a different molar heat capacity. So, how much heat is absorbed by a copper penny with a mass of 3.10 grams, whose temperature rises from -8 degrees Celsius to 37 degrees Celsius? Copper, we're telling you the specific heat, is 0.385 joules per grams degree Celsius. We're simply going to use the heat capacity equation, where it's the specific heat, which was given to you, the mass, we know it was in the problem given, 3.10 grams, and the change of temperature. We are simply going to plug and chug. That is it. Okay? Once you plug and chug, you can see that 0.385 times 3.10 times the change in temperature, final minus initial, okay, we get 53.7 joules. And you'll note from the units of the specific heat, joules per gram degree Celsius. This was grams, so that would have canceled. This was degrees Celsius, so that would have canceled. All you were left with was joules. Here, calculate the amount of heat released when 7.40 grams of water cools from 49 degrees to 29 degrees Celsius. You were given water specific heat. I'm telling you, you need to memorize water specific heat. You need to know that. You will not be given that. Pause this, take a minute, see if you can figure it out. Here it is. Same equation. Q equals the specific heat times the mass times the change in temperature. Negative 618.64 joules. With significant figures, 620 joules. So, when we look at this, it's important to understand this conceptually. You're going to be asked stuff like this, similar to this. So a piece of metal at 85 degrees Celsius is added to water at 25 degrees Celsius. The final temperature of both the metal and the water is 30 degrees Celsius. Which of the following is true? Heat lost by the metal is greater than heat gained by the water. Heat gained by the water is greater than heat lost by the metal. Heat lost by the metal is greater than heat lost by the water. Heat lost by the metal is equal to the heat gained by the water. More information is required. How many of you guys want to pick number 5? Okay, so let's look at this. The answer is number 4. Keep hitting the wrong button. Sorry, guys. Why? Heat lost by the metal is equal to heat gained by the water. How do we know that's true? We know it's true because the system is the metal, the water is the surroundings. Whatever heat is lost by the metal is directly absorbed by the water. It's always true that heat lost must be equal to heat gained. Energy in equals energy out. There's no greater than or less than. Energy is neither created nor destroyed. The overall energy must be maintained. Okay, I'm going to ignore some of these examples because I want to work some of these in class. Not these, but different problems in class. Okay, let's stop here. Hold on. Hang on one second, maybe not. Okay, we're going to do this pressure and volume work, and then we're going to stop and we'll work problems on Thursday. So when we talk about, we already talked about work being equal to the force times the distance. But now if we talk about expansion work, it's something very different. Okay, so when we look at this, you need to think of this in terms of like pistons. You know how they, or not even a piston, but like maybe the arm of the screen door that keeps it from slamming, where when we push it in, it gets kind of slower and tighter, and pull it out, it gets kind of larger and easier to work. So the expansion in the volume, it creates an atmospheric pressure outward, and it just works differently. There's more pressure involved. And if we're looking at these pressures, what we're looking at is force over the area. So whether or not our area is smaller or larger, then it's going to affect the pressure. I think innately we kind of understand this and know this. So what they're showing you here is that this is before the reaction, the initial state. After the reaction, you have clearly a distance here. And this distance has increased the total volume. So when we look at the volume changes, we can look at it in terms of work. Work is force times the distance. We also know that's also equal to the negative pressure times the area times the distance. It's just another way of rewriting this, because force is pressure times area. Pressure is force divided by area. So we can kind of negate this down to work equals the negative pressure times the change in volume. We're not going to do these exercises, but we'll look at this one. So all this says is a balloon is inflated from 0.1 liters to 1.85 liters against an external pressure of 1 atm. How much work is done? They are giving you that 101.3 joules is equal to 1 atm liter. So if the equation is work is equal to the negative pressure times the change in volume, here's our change in volume, here's our pressure, then we simply plug and chug and do the math. Okay? Once we have this, we can just convert to joules and get a negative 177 joules. All right, we're going to stop there for tonight, and we're going to work problems tomorrow. I'll put another one of these up over the weekend, and we'll just work problems on Tuesday. If you have any questions, email me. Thanks, guys. Good night.